สวัสดีค่ะยินดีต้อนรับทุกท่านเข้าสู่ไทยซิกไคซิมโพเซียมครั้งที่3นะคะสำหรับธีมในปีนี้นะคะก็จะเป็น Human Computer Interaction and the New Realities นะคะซึ่งเราจะจัดในวันที่ 21 และ 22 มิถุนายนนะคะโดยการไลฟ์อยู่บน Facebook Bangkok SM SIGCHI Chapter ค่ะสำหรับปีนี้นะคะเรามีวิทยากรรับเชิญนะคะถึง3ท่านด้วยกันนะคะท่านแรกก็จะเป็น Professor Mark นะคะที่จะมาบรรยายในวันนี้นะคะแล้วสำหรับวันช่วงคนที่2นะคะก็จะเป็นคุณอภิรักษ์นะคะแล้วก็สำหรับวันพรุ่งนี้ก็จะเป็นคุณประธานนะคะแล้วก็ต่อด้วย Research Showcase นะคะก่อนอื่นจะขออนุญาตแนะนำนะคะให้ได้รู้จักกับBangkok SM SIGCHI Chapter ของเราก่อนนะคะว่าเป็นกลุ่มที่เกี่ยวกับอะไรนะคะค่ะ Bangkok SM SIGCHI Chapter หรือเรียกสั้นๆกันว่า BKK SIGCHI Chapter นะคะเป็นกลุ่มที่สร้างขึ้นสำหรับคนที่สนใจในงานวิจัยทางด้าน Human Computer Interaction นะคะ Human Computer Interaction คืออะไรนะคะก็คือการปฏิสัมพันธ์ระหว่างมนุษย์กับคอมพิวเตอร์นะคะซึ่งในสาขาวิชาทางด้านนี้เนี่ยก็จะครอบคลุมความรู้ในด้านต่างๆนะคะอาทิเช่นประสบการณ์ของผู้ใช้หรือที่ปัจจุบันเรียกกันสั้นๆนะคะว่า UX หรือ User Experience นะคะและอีกในด้านหนึ่งนะคะก็คือความเหมาะสมต่อการใช้งานนะคะ Usability หรือการออกแบบปฏิสัมพันธ์นะคะ Interaction Design ค่ะโดยนะคะ BKK SIGCHI Chapter ของเราก่อตั้งและดำเนินการโดยคนไทยนะคะทั้งที่อยู่ในประเทศไทยแล้วก็ต่างประเทศทั่วโลกนะคะซึ่งเราได้รับการรับรองและสนับสนุนเครือข่ายนานาชาติด้านสาขาวิชาปฏิสัมพันธ์ระหว่างมนุษย์กับคอมพิวเตอร์ในสมาคมคอมพิวเตอร์ ACM นะคะค่ะโดยเป้าหมายหลักของเรานะคะอย่างแรกเลยเราอยากให้เกิดการแลกเปลี่ยนความรู้ข้อคิดเห็นและประสบการณ์เกี่ยวกับการวิจัยการเรียนการสอนการทำงานในด้าน SCI ทั้งในประเทศไทยนะคะหรืออาจจะเป็นสมาชิกที่ทำงานอยู่ที่ต่างประเทศนะคะในระหว่างสมาชิกของกลุ่มของเรานะคะ2ก็คือการจัดกิจกรรมหรือโครงการต่างๆเพื่อส่งเสริมและช่วยให้สมาชิกของกลุ่มสามารถสร้างสรรค์ผลงานนะคะหรือผลงานวิจัยทางด้าน HCI ให้เป็นที่ยอมรับในระดับนานาชาติค่ะจะขออนุญาตแนะนำนะคะสมาชิกหรือว่าทีมงานของเรานะคะค่ะก็ดิฉันนะคะโอชินนะคะหรือศิลานีนุชิประสิทธิ์ชัยนะคะเป็นประธานในปีนี้นะคะแล้วก็รองประธานคือยืนยงนิสยามนะคะแล้วก็มีเฮเลนยิกนะคะคุณกิตยาทองผาสุขนะคะแล้วก็มีเว็บมาสเตอร์คุณมินตราเลื่อนสุขนะคะแล้วก็เลขานุการคุณลำพาพันธ์พันชูจิตนะคะและเราก็ยังมีทีมงานหลักอีกหลายท่านนะคะคุณทิพยาจินตโกวิทนะคะคุณกรันวรพงศ์สิทธิกุลคุณสุพรพงษ์นุ่มกุลนะคะคุณอาทิมาธาราทิพยกุลนะคะคุณนวลพันธ์แก้วผนึกรังสีคุณชัชวาลวชระมโนธรรมคุณสลินทิพย์สุดสงวนและคุณธันมาทิพย์เปี่ยมสมบูรณ์นะคะค่ะโดยทุกท่านสามารถติดตามข่าวสารกิจกรรมต่างๆได้ผ่านบนเว็บไซต์ของเรานะคะก็คือ Bangkok SM SIGCHI Chapter ค่ะและที่เรากำลังจัดกิจกรรมกันอยู่ในขณะนี้ก็จะเป็น Facebook ของเรานะคะทุกท่านสามารถกดไลค์กดติดตามได้นะคะที่ Facebook bkk.sigchi ค่ะหรือว่าท่านใดที่สนใจนะคะอยากจะได้รับข่าวสารอย่างต่อเนื่องนะคะสามารถสแกน LINE QR Code ได้นะคะจะเป็น Thai SIGCHI Community LINE นะคะค่ะโดยกิจกรรมที่ผ่านมาของ Chapter เรานะคะก็จัดกันอย่างต่อเนื่องเป็นประจำทุกๆเดือนนะคะก็จะเช่นนะคะเป็นการจัด Book Club นะคะได้มีการอ่านหนังสือทางด้านของ HCI ที่น่าสนใจหลายอย่างแล้วเราก็ได้มีการมาแบ่งปันมุมมองกันนะคะค่ะแล้วก็ในบางครั้งเราก็มีโอกาสนะคะจัดแบบพบปะเจอหน้ากันบ้างนะคะก่อนที่จะเกิดสถานการณ์โควิดนะคะซึ่งตอนนี้เราก็คิดถึงสมาชิกหลายๆท่านค่ะแล้วต่อมาเนี่ยนะคะเราก็ได้ทำการปรับ รูปแบบของเรานะคะจาก Book Club มาเป็น Journal Club ค่ะซึ่งอันนี้ถ้าท่านใดสนใจสามารถเข้ามาร่วมจอยได้นะคะตอนนี้ก็มีนักศึกษาในระดับปริญญาตรีแล้วก็ระดับปริญญาเอกที่ได้เข้ามาร่วมแลกเปลี่ยนรับฟังความคิดเห็นความรู้กันนะคะค่ะโดยที่ว่าล่าสุดอันนี้นะคะเราก็ได้มีการพูดถึงในบทความของ Tangible Circuit นะคะเป็นอะไรที่น่าสนใจนะคะที่เขาใช้นวัตกรรมของ 3D Printing เนี่ยเข้ามาช่วยในการพัฒนาสื่อการสอนทางด้านของ 3D Printed Circuit นะคะค่ะค่ะแล้วก็เราก็ได้มีโอกาสนะคะทำในส่วนของจัดเวิร์กช็อปหรือการฝึกภาคปฏิบัติให้กับหน่วยงานต่างๆที่ติดต่อเข้ามานะคะอันนี้ก็จะเป็นการจัด UX UI นะคะเวิร์กช็อปให้กับนักศึกษาที่มหาวิทยาลัยราชภัฏอยุธยานะคะค่ะเราก็ได้พานักศึกษาเนี่ยออกไปเก็บข้อมูลในภาคปฏิบัติเลยนะคะที่ศูนย์ความสัมพันธ์อยุธยานานาชาติค่ะซึ่งเด็กนักศึกษาหลายกลุ่มเนี่ยทำให้เกิดไอเดียบันเจิดมากมายนะคะหลังจากที่รับฟังเพนพอยต์นะคะจากทีมงานที่ทำงานในศูนย์นะคะจนอาจารย์ก็ได้พูดคุยว่าสงสัยเด็กๆจะมีโปรเจกต์ได้ทำจบกันหลายงานเลยนะคะค่ะและเราก็ยังจัดกิจกรรมนะคะเพื่ออัปเดตความรู้ของเรานะคะแล้วก็แลกเปลี่ยนประสบการณ์ให้กับกลุ่มสมาชิกอันนี้ก็ในส่วนของ Design Thinking Workshop นะคะโดยอาจารย์ทศพรสายยิ้มนะคะค่ะและนี้ก็จะเป็นการจัดUX and UI Design for Digital Innovation ให้กับนะคะนิสิตนักศึกษาของคณะวิศวกรรมเครื่องกลมหาวิทยาลัยเกษตรศาสตร์นะคะมีทั้งการบรรยายแบบภาษาอังกฤษนะคะที่เป็นน้องๆหลักสูตรอินเตอร์นะคะแล้วก็มีเป็นหลักสูตรภาษาไทยนะคะน้องๆก็ได้มีการลงมือทำภาคปฏิบัติได้ลองดูว่าการออกแบบนะคะ UI เป็นยังไงบ้างนะคะแล้วก็การเก็บuser experience เป็นอย่างไรบ้างนะคะค่ะแล้วก็รางวัลที่ผ่านมานะคะเว็บไซต์ของเราก็ได้ที่1นะคะจากการประกวด SIGCHI Chapter Website Competition ค่ะอย่าลืมเข้าไปแวะชมเว็บไซต์ของเราด้วยกันนะคะค่ะแล้วก็ถ้าท่านใดนะคะสนใจที่อยากจะสมัครเป็นสมาชิกของเราสามารถสแกน QR Code ได้นะคะโดยที่ว่าจะเสียค่าสมัครสมาชิก500 บาทตลอดชีพนะคะเพียงครั้งเดียวค่ะนะคะหลังจากนั้นเนี่ยท่านก็จะได้รับเสื้อ Bangkok ASEAN SIGCHI Chapter นะคะจะส่งไปให้ตามที่อยู่ที่ได้ให้ไว้นะคะแล้วก็จะได้รับส่วนลดนะคะในการเข้าร่วมอบรมคอร์สต่างๆนะคะแล้วก็ได้รับสิทธิ์ในการลงทะเบียนเข้าร่วมงานต่างๆนะคะและรวมถึงการเข้าร่วมงาน Symposium ที่ไม่มีค่าใช้จ่ายนะคะแล้วก็การประชุมประจำปีนะคะสุดท้ายนี้เราขอบคุณสปอนเซอร์และพาร์ทเนอร์ที่ผ่านมานะคะที่ได้มีโอกาสร่วมสร้างสรรค์ทำให้งานวิจัยทางด้าน HCM ในประเทศไทยเนี่ยได้มีการพัฒนากันอย่างต่อเนื่องนะคะขอบพระคุณค่ะในลำดับถัดไปนะคะก็จะเป็นการบรรยายพิเศษค่ะขอเรียนเชิญอาจารย์แทมเลยค่ะ
ครับผมสวัสดีครับผมธรรมทิพย์นะครับก็จะแนะนำ Professor Mark เป็นภาษาอังกฤษนะครับ So it is our great honor to have an ACM distinguished speaker, Professor Mark Billinghurst, as our keynote speaker today. Mark is Professor of Human-Computer Interaction at the University of South Australia in Adelaide and Professor in the Bioengineering Institute of the University of Auckland, New Zealand. He earned a PhD in 2002 from the University of Washington and is well known for his research in augmented reality, publishing over 450 research papers in the field. He previously has researched topics such as variable computing, mobile interfaces, collaborative systems, and virtual reality, and is currently exploring empathic computing as well. Prior to his current role, he was director of the HIT Lab New Zealand at the University of Canterbury, and he has previously worked at British Telecom, Nokia, Google, and the MIT Media Lab. He has received many awards, including the 2013 I2B VR Technical Achievement Award for contributions to research and commercialization in augmented reality. And in 2012, the 10-year Lasting Impact Award for the most influential paper published at the ISMA conference in the past 10 years. In 2013, he was elected as a fellow of the Royal Society of New Zealand. Mark has been a member of the ACM for over 15 years and has been involved in a number of roles, including program chair for the ACM IUI conference, MGIA chair at SIGCHI Asia, emerging technologies chair SIGCHI Asia, and many review and program committees. He is also a senior member of I2B and has heavy involvement in organizing the I2B ISMA conference, including being the previous conference chair and the current steering committee chair. The topic of Mark's keynote today is augmented reality, the next 20 years. So without further ado, I hand over to you, Mark, if you would like to share your screen.
Great, thank you very much for the introduction, and I'm sorry I cannot be there with you in Bangkok, in Thailand. It's one of my favorite cities, but hopefully in the future I'll be able to travel again. So let me share my screen here, and just go to the full screen. Just 1 minute. Great. I hope you can all see that. What I'm going to talk about today is augmented reality and some technologies that will impact augmented reality over the next 20 years. But first of all, I want to talk a bit about the past. So, for example, the year that I was born, 1967, this was the most popular computer in the world. This is the IBM 1401. And half of the computers in the world at that time were this computer. You can see it takes up a whole room, actually almost the size of a house. And it costs $10,000 a month to run. And $10,000 a month, this was the rental price. You could not buy the computer, you had to rent it. And that was actually the same price as a house in 1967. So very huge, expensive machines. Of course, since that time, computing has changed a lot. And now we have got to the point where you have the Google Glass display. So you have a small computer that can be on your face. And this was from 2013. So we've had the computer disappearing, going from room-sized computers in the 1960s to on the desk in the 1970s, and then the lap, and then the hand, and now in 2010s, it's on the head and kind of disappearing into the real world. But the interfaces themselves haven't really disappeared as much. So this is a traditional computer interface where you have a graphical user interface, and you have the separation between the real and digital world. So you can see on the top right-hand corner, there's a picture that shows the C, which is digital domain, and the R, which is the real world, and there's this kind of gap, between what's on the screen and what's in the physical world. So one of the main trends with user interface design is to try and make that interface disappear. And there are several ways you can do that. So this is a nice graphic that I took from Professor Jun Okamoto's paper. And he talked about how you could make interfaces invisible by embedding the person inside the interface through virtual reality, by making the computer go away through Internet of Things, or through augmented interaction. So I'll talk about those a little bit more. So first of all, Internet of Things. So many of you are familiar with devices like the Amazon Alexa or the Nest thermostat. And so the Internet of Things is we try and embed computing and sensing into the real world with smart objects and smart sensors. And so because of that, the computer really disappears. It becomes part of our real environment. Another way of making the computer go away is through virtual reality. And with virtual reality, people typically wear head-mounted displays and use gloves or body tracking to be able to completely replace their real world with computer graphics. And the key features of virtual reality really is around immersion, interaction, and imagination. So here's a video showing this working. And this is a person that experienced virtual reality the first time. So you can see in this video, he is interacting with a little robot, and he's using his hand gestures and computer graphics. This is really typical of a virtual reality experience. Oh, I wanted to check actually, Sam, can you hear the audio okay from the video?
Yep, it's great. It's
good,
very.
okay.
Oh no, well, wait for the video. Could you please
Yes.
just increase the?
Oh, well, next time. I just want to make sure you're getting some
All right.
audio because, yeah. So that's a typical virtual reality system. And, but what we're mainly going to talk about today is augmented reality. And the idea with augmented reality is, again, to make the computer disappear. But in this case, using see-through displays or handheld displays to allow virtual content to become seamlessly part of the real world. So the idea is to increase your interaction with the real world, but have that interaction mediated by a computer. And so there are really three key elements of augmented reality. First of all, it combines real and virtual images, so they both can be seen at the same time. Secondly is that it's interactive in real time, so the virtual content can be manipulated. And then thirdly, so that the content appears registered in the real world, so the visual objects appear fixed in the real world. So a good example of a typical augmented reality system is this application here from a spin-out company from my previous lab called Quiver. And in this company, you can take the McDonald's playmat and you can color it with your own color pencils. And then when you look at the playmat with your mobile phone, you can see the virtual objects come to life. So you can see now there's a little virtual character, and the character can dance and perform some actions. The most important thing, though, is that this character takes the colors that you have applied yourself. So it kind of creates a magical connection between the person and the graphical content. And so this is a typical augmented reality scene where you can see the virtual content appearing to be fixed in the real world. So here's the character, looks like it's dancing on the table. So you can arrange those three types of interfaces on this continuum. So depending on how much of your user experience is generated by the computer. So on one end, on the right-hand side, there's immersive virtual reality, and this is where, of course, the computer is immersing you completely in graphics. On the left-hand side is the Internet of Things. In this case, the computer doesn't replace any of your real world, and then augmented reality sits in the middle. And this oftentimes is called the mixed reality continuum, which was a term coined in 1994 by Paul Milgram, where he talks about how the mixed reality allows you to replace elements of the real world. About the same time as the IBM 1401 was being developed, Ivan Sutherland invented the first head-mounted display with computer graphics. You can see him wearing the system here. He has this display on his head, and through that display, he could see a cube appearing. So this is an amazing accomplishment. Of course, you remember the computers were the size of a house, and they were mostly using punch card or keyboards to interact with. And at the same time, he had this vision of computers that where you were able to interact with using computer graphics. So augmented reality might seem like a good choice of, it might seem like a modern technology, but actually it has more than 50 years of history behind it. And over those 50 years, we've seen the first head-mount displays through to being used in the military, then outdoor systems, and finally on mobile phones, which means now that if you have a mobile phone in your pocket, almost everybody can have an augmented reality experience with that. So it becomes widely available. So augmented reality today has many, many application areas, from design, you can see here, to interior furniture layout, to outdoor navigation, or other application areas as well. And in fact, the business is growing very, very strongly. The predictions is that last year it was more than $7 billion of US business, and this year it's going to be more like $10 to $12 billion. And there are many, many available devices for delivering augmented reality applications, such as head-mount displays or phones or tablets, or head-up displays in cars. We also have a lot of tools for developers that makes it very easy to build augmented reality systems. And there are many large number of applications. If you go onto the mobile app store, you'll see tens of thousands of augmented reality applications. And finally, there's a very strong business and research community, there's the ISMA AR conference, which is really popular, the website augmentedreality.org, which connects companies together. And so it's a very thriving community. So, but what we want to talk about today, though, is really where we're going from here and what's happening in the future. And so the physicist Neil Bohr says that prediction is very, very difficult, especially about the future. And so he's kind of, he was talking about how difficult it is to take today's technology and project where it's going to be in the future. But luckily, we don't need to do that. The famous many companies, many companies create concept videos of what they think the future is going to be like and make their own predictions. So in this video from Samsung, you can see the person wearing these small glasses and using them to conduct a remote business meeting. And then he pulls the people inside the virtual building to show them an immersive VR experience. And then when he's finished that, he can just walk away. So it's kind of a concept video to show where augmented reality can be going in the future. And these types of things enable us to explore the user experience around augmented reality. Oh, sorry, I just went back too far. So Bill Buxton made the very famous statement about 15 years ago, saying that the technologies that will significantly affect our lives over the next 10 years have been around for a decade, and the future is already with us. The trick is learning how to spot it. So he's saying that instead of taking technologies now and extrapolating them out into the future, what we should be looking at is what's already been around in the labs and see how they can be taken from the lab out into the consumer environment. So what I want to do today is talk about some technologies in augmented reality that have already been around for a few years and where they might be affecting us over the next 10 to 15 years. So first of all, to go back to some key enabling technologies. In the beginning of the talk, I talked about how augmented reality combines three things: the real and virtual images, they're interactive in real time, and the content is registered in 3D. And each of these things talk about or provide some requirements for the technology that's needed. For example, combining real and virtual images means you have to have some sort of display technology. If things are interactive in real time, you need some interaction technologies. And if the virtual content appears fixed in the real world, like you saw with the happy dancing McDonald's character, you need some tracking technologies of being able to place, know where the user is looking from, so you can place the virtual content in the real world. So I want to talk about each of these three areas and some interesting trends in those areas that may affect augmented reality. So first of all, display technology. So I already showed you the picture of Ivan Sutherland's display from the 1960s. And so in the past, we had these very bulky head-mount displays, and currently we have some quite light weight head-mounted displays or handheld displays like mobile phones or tablets. And what we'll see in the future is we'll see more wide field of view see-through displays, projected AR, displays where you can project onto the retina, and also contact lenses that you can use to have an AR experience that makes it very socially acceptable. So here's an example of a typical display from this year. Actually, this is from last year, the North Focal's display. These are a very small field of view display, but they're almost indistinguishable from a pair of glasses. And they also combine that with a ring input device. This shows what's currently available by using thin waveguide glasses. So this is the technology which is now being put into displays. And by building these waveguide glasses, you can build very socially acceptable displays. But the field of view of those displays is quite low. The North Focal's is around 10 degrees, and many of them typically have a 20 to 30 or 40 degree field of view. So there's some research being done from University of North Carolina and from NVIDIA to look at how you can build wider field of view displays. And the pin-like display at the bottom is an example of that. In this case, they take a piece of glass, put small pinholes in it, and they work as little lenses, and they can widen the field of view. So this video here shows the view through those displays. So you can see here they have this very wide field of view, and the field of view on these displays is 110 degrees, which is much wider to work with than the normal display, like a whole lens or something else like this. That same approach is now being used in some commercial displays. So this is a display from a company called Kura, and they again use those pin points to create a wide field of view, and their display is 150 degree field of view. And you can see from this picture they also have very transparent lens, and they provide high resolution of between 4 and 8K resolution. So very interesting AR display. One of the more interesting areas for augmented reality is looking towards contact lenses, where you don't need to wear a pair of glasses at all. In 2008, Babak Parvez from University of Washington developed the first contact lens display that can provide power and data into the eye. And there's a company now called Mojo Vision, which has raised significant amounts of funding to build a smart contact lens that can fit into the eye. And so this is the evolution of the Mojo lens display. And so they built their first prototype in 2017. And then over the 4 years since then, they've enhanced it. And now they said that in later this year or early next year, they'll bring out their first product, which is going to be a display for people with low vision. So to show you this working, let me just show you a bit more about the details. The display has really 4 pieces. It has a electronics package in the middle here that combines power and sensors and communication. There's a prescription lens on the bottom so people can wear it with a normal prescription lens, and a cosmetic iris, and that allows the contact lens to look like a natural contact lens, natural eye, and there's a plastic protector at the top of that. So let me show you a little video of the people talking from Mojo about this product.
Building the world's first AR contact lens is a systems engineering problem, and therefore we've had to innovate in many different areas. For example, displays, optics, wireless communications, sensors, and materials, all while keeping the system small, low power, and of course safe. We embed all of our smart components into a time-tested contact lens platform called a scleral lens. A scleral lens rests on the white part of your eye, and it doesn't touch your cornea. What we do is we custom fit each lens to your eye so that it's extremely comfortable to wear and doesn't rotate or slip on the eye. We've also patented a method that maximizes the oxygen delivered to your eye, which is another critical element of contact lens comfort and eye health. The Mojo lens includes thin film, biosafe batteries to power the system, as well as motion sensors to enable the world's most accurate eye tracking. We've also developed an extremely low power image sensor that's used for computer vision and scene detection. But at the heart of the Mojo lens is the world's smallest and densest dynamic display. The pixel-to-pixel spacing in our display is only 1.8 microns, giving it a density of 14,000 pixels per inch. With this, we can display crisp text, photos, and video in a package that's less than 0.5 millimeter in diameter.
So I won't show the rest of the video, it's quite long, but you can see from that they've developed a really amazing display technology. They can squeeze down into a small display they can put into the contact lens, and then they combine that with some eye tracking technology and other technologies to provide a AR experience. So they're going to bring this to market next year. The first market will be for people with visual disabilities, but then after that they'll be able to develop a fully fledged AR display for contact lenses. So that shows you some trends happening in the display space. I want to talk now a little bit about the interaction space. And with augmented reality, in the past, interaction was fairly limited. So you can see the top picture here shows a handheld display. And as you look with that at a poster, you can see some image content popping up. And this was mostly limited just to manipulating your viewpoint and changing where you're looking. But now there's much richer interaction by using touchscreen input on the phones, or simple gestures, or tangible interaction. And in the future, you'll see a lot more intelligent interfaces, very natural hand gestures, combining speech and gestures together in multimodal input, and also using physiological sensors as well. So to give you some examples of some of these, one of the very exciting trends now is looking at using natural gesture interaction with augmented reality systems. So a number of researchers have been looking at how you can use depth sensors for capturing gesture, or how you can use just natural cameras themselves, and by doing that, capturing rich two-handed gestures. So Microsoft Research, for example, produced a very nice hand tracker, and they're now being hand input and combined into commercial systems like the HoloLens 2 or the Oculus Quest 2. To show you some examples of this, this is a video from the SIGCHI Asia conference last year that shows real-time tracking, hand trackings from a monocular camera. So just using a single camera, single color camera, they can track the hands in 3D. I'm just going to fast forward through this because it's quite long, but the second part of the video shows how you can, oops, it's a bit too far. Right. So on this part of the video here, you'll see on the right-hand side their hand tracking system, on the left-hand side one of the leading competitors, and you can see the virtual hands overlaid on the real hands on the camera view, and the person is able to perform quite good hand gestures and also occlusion as well, and being able to cover one hand with the other hand and being able to interact together. So you can see here an example of occlusion where they've got two hands coming together and still being able to track quite well. And I'll just fast forward a little bit more, and you can see here some examples of the hand tracking being used in some simple applications. So the person there is placing some objects, cards on a table. They're overlapping their fingers, they're tracking, moving their hands in front of one another. So once you can track the hand positions, you can use some very interesting ways for input into augmented reality. And this next little video shows an example of that. So you can see this is an augmented reality display, and on the real hand you can see a virtual menu appearing, and then you can flick the menu tabs with your other finger, and even pull the menu out. So it shows a nice example of a natural interface with two hands for augmented reality using gesture tracking. And in fact, Microsoft has, they're using a depth sensors in their Microsoft HoloLens, but they've created a whole user interface design around hand gesture input. So the next video shows the, oh, did I miss it? Oh, I'm sorry, I didn't put that video in. I was going to show you the video from the MRTK, but I left that video out. Anyway, so with that hand tracking, that works very well, but hand tracking with cameras is very good for large types of gestures, but it's very hard to measure very fine gestures. So in some of the research that we did a couple of years ago, we looked at how we can combine different gesture types together. So we used the Leap Motion, which is an image sensor system to track the hands with large gestures, but we then used the Google Solely to do fine scale hand tracking with radar sensing. And so this meant you could combine both a large motion and fine tuning motion to support very natural interaction on multiple scales. So let me show you a little video of this working. So in this video, you can see here the Leap Motion being used for large macro scale gestures, and then the Google Solely for micro scale gestures. So for example, you could use the hands to grab an object and move it around. But once the object is placed roughly, then you can use the very fine stroking on your fingers to exactly place the object and align it like you want with the virtual target. So this shows you the benefit of combining two different hand tracking systems together. Here's another example of virtual puppetry, where you can see a virtual puppet appearing in AR, and as you move your fingers around, you can make the puppet walk in the direction that you're looking, and you can control the animation speed of the puppet as it starts moving around. So that's hand tracking input, and we'll start to see a lot more natural interaction techniques using both hands in the coming years. Another very exciting area is eye tracking input, and there are a number of head-mount displays now that have integrated eye tracking into them, like the HoloLens 2. There's a number of research questions that should be addressed, such as, how can eye gaze be used for interaction? What interaction metaphors are the most natural? And so, again, a couple of years ago, we did some research to explore that, and in particular explore using implicit versus implicit input, gaze input. And so we want to explore different gaze interaction methods. And one interesting method that DAM came up with actually is this method called dual reticles, where you have two different reticles that are used for the eye tracking input. And I'll show you that in a minute. And this was used using a HTC Vive head-mount display with the pupil labs for eye tracking. And the basic idea of the dual reticles was that when you look around, you have one eye reticle that follows your eye gaze very quickly. But there's a second reticle that lags behind. And when your eye dwells on an object, the two catch up, and when they catch up, then you cause a selection with that object. So you can see in the first picture here, the yellow real-time reticle, and this one follows your eye very quickly. And then you have this inertial reticle, which is the green one that lags behind. And when you dwell on a object, then the two catch up, and after a small amount of time, they cause the object to be selected. So let me show you a video of this working. So you can see here's a picture on the wall of lots of tanks, and the person is looking around, and the yellow eye gaze is moving very fast with his eyes. And then the green reticle is the inertial reticle that drags behind. And as he gazes at certain vehicles, the green one will align with the yellow one and become selected. So this is one method that could be used for doing eye gaze selection in AR. And this is important because with eye gaze, of course, you're always looking. And so one of the problems that they have with eye gaze input is what's called the Midas touch problem, where you may be trying to select everything you're looking at all the time, which doesn't work very well. Eye gaze is one example of a physiological sensing input you can use, but there's a lot of other examples you could use as well. So in our lab now, we're doing some interesting research on how we can use a range of different physiological sensors for implicit input and developing systems that recognizes the user's intent or activity. And two of those, for example, is EEG, measuring the brain activity, and also EMG, measuring muscle activity. So for example, here's an example of an EMG sensor. You put this little brick on your arm, and you can measure the muscle activity. When the person tenses their hand, you can see it's getting a strong signal from the EMG sensor. And then this could be used in an AR interface to trigger certain events. So here's a person wearing the Microsoft HoloLens, and can see these boxes, and when he makes a gun shape with his hand and makes the fist, it's going to send fireballs out in the direction he's pointing his hand. So just by tensing his muscles, he can start interacting with the augmented reality content. One of the other areas which is very exciting is EEG measures and using brain activity to measure augmented reality or cause augmented reality commands. And so this is from a company called NextMind, and NextMind provide an EEG attachment for AR and VR head-mount displays. So you can see on the picture there's a piece of plastic attachment that has 8 electrodes, actually 9 electrodes, sorry, mounted on it, and then you attach it to the back of your head-mount displays, and then you can measure people's brain activity through these electrodes. So here's an example of the system working. You'll see a person playing a game, and as he looks around in the VR headset, when he concentrates, he's able to send kind of a mind wave in the VR environment to destroy these creatures that are coming to attack him. But this is all done through concentration. There's no physical input with handheld controls or anything like that. So you can see he's just looking and then concentrating, and he's able to send a little kind of wave through and knock the creatures out. You can also concentrate and jump into the next room. And one of the other areas that we've been looking at is combining the multiple input streams together. So I already showed you about using gesture input inside augmented reality. And gestures are very good for grabbing and manipulating objects. So they're very good, and also very good for qualitative input. So making a handshake with gestures, for example. But it's very hard with gestures to specify things like numbers or color. And so speech is very good for that. And so if you combine them together, you can provide very good commands using multimodal input. So for example, commands like put that there when you're pointing at an object. So Tham, when he was doing his PhD at the Hit Lab New Zealand, developed some multimodal input systems where you can combine hand tracking and speech together, and you fuse the speech commands and gesture commands to create a single command line, which is more accurate than either alone. And what we found by doing that is that we could complete tasks much faster with multimodal input, and also with much less errors. So here's a video of the system working. So you can see Tham giving some speech commands and then using hand gestures to manipulate objects. So this is a speech and multimodal input design system. So he's saying extruding a solid, he draws a shape, and now a solid with that extrusion will appear, and then he can move it around using his hand gestures or stretch it or manipulate it.
Release.
So with that system, we found that you could very easily use speech and gesture as a complementary way. This is one of the other areas that we've been working on is how you could actually use intelligent agents to collaborate with you in augmented reality to help you improve tasks better. This is particularly important for training tasks. And this is where you want to move from implicit input to explicit input, where you have a system watching the user and then responding to what they're doing to create some intelligent feedback. So they can recognize users' behavior and then create adaptive feedback based on the users. So about 5 years ago, we developed an AR intelligent training system where we looked at combining intelligent tutoring with, on the back end, with augmented reality for visualization. And we're focusing on PC assembly. So the person would start to have to assemble a PC. And if they made any mistakes, the AR system would provide corrective feedback. So we had some system that could track the real components of the PC when you put them in the wrong order, or when you manipulate them in some wrong way, then the computer gives feedback. And we found that by using the intelligent tutoring, we were able to complete the PC assembly about 30% faster. And then more interestingly, about a week later, people had about 25% better retention of the knowledge they'd learnt than without having the ATS or the AR ATS system working. So here's a video of the system working. And you'll see in this video, person picking up some components. Oops, I'm sorry, it looks like the video in this case is not linked. Oh, well, I can talk about the interface. So this is what the interface looked like. And as the person picked up and moved components, then these virtual arrows would appear showing them where they should be placed and gave intelligent feedback. One of the new things, though, is one of the issues with this type of interface is how do you represent the computer? And in this case, we just had the computer as a disembodied kind of line of text appeared on the screen. But more recently, people have done some research looking at how you can have a virtual agent to represent the computer. And in this video here, you'll see a virtual character appearing. And this virtual character has the intelligence, and the person uses speech to interact with the character, and the character responds in an intelligent way. So let me just go back and show that video working. So first of all, the person places the character on the chair there. The character walks over and will sit down on the chair, and then it will start talking to the person.
Thank you.
So you can see there's a virtual character that recognizes speech and can also respond in an appropriate way. The other thing that you may have noticed is as the person's walking around, the character always turns to look at the person as they're moving. So it shows some intelligent behavior as well. So the last technical thing I want to talk about is tracking systems. And so in the past, we had simple marker-based tracking for augmented reality using computer vision, or using GPS for location tracking, or magnetic and mechanical tracking. And now we have much more sophisticated computer vision systems. But in the future, we'll see a lot more ubiquitous tracking or model-based tracking, or even tracking from objects in the environment. So as an example of model-based tracking, this is where you know the 3D shape of an object you want to track from, and then you use that to find the position or pose of the real camera. One particularly exciting area of this research is being able to track from deformable objects. So for example, cloth that you can bend and deform. So this video here shows a piece of paper that's being deformed, but on the right-hand side, you can see the virtual tracking from that paper. So even though the paper's been bent around, the AR system can still track that deformation, track the camera position with respect to that piece of paper. In recent years, there's also been research done on environment tracking. And so this is where you can scan your real environment and using depth sensors or other technology. And then once you've built that 3D model of the environment built up, you can then use that to track a virtual camera position. One of the nice examples of that is in the iPad Pro. So the recent iPad Pro has a LiDAR scanner in it, and it can scan up to 5 meters away and create models of the real person's environment, and then use those to track the position of the iPad relative to the real environment. So here's an example of a scanning app using the iPad Pro. So they can scan around and they're capturing that geometry using the laser scanner. At the same time, they're also capturing, using the camera, some visual feedback, and they can combine the two together. You can see how they can now create a 3D model of that library room. And here's using the same technique to capture a 3D model of this this tractor digger here. You can see the model's quite accurate. It's even able to capture graffiti on the wheel of the tractor. And here's another example of being able to scan a skull. So these types of research allows us to do tracking from almost any real-world environment. Microsoft a couple of years ago showed how you can combine together input from several depth sensors to create and to do dynamic reconstruction. So unlike just tracking furniture and heavy machinery that is fixed, this allows you to track from dynamic moving surfaces. So in this case, you can see there's a dancer there, and the system is tracking the cloth that she's of her skirt as it moves around. So I'll show you a little video of this working here. The way the system works is it has multiple depth sensors. So you can see the person doing some karate, and on the screen there you can see the final output. So, and especially note how he moves around the clothing. It looks very realistic and deforms and responds in the same way. So on the left-hand side is the input data coming from the depth sensors, and on the right-hand side is the final output. And the way this works is that the system takes several cameras, and then from each of those cameras, it segments out the user from the background. And then it looks for corresponding points on each of those images and combines them together into a point cloud. And then it also cleans up the data because it's quite noisy. And so it looks for other points that aren't related. And then it uses some machine learning techniques to create a final fused data set. You can see on the right-hand side there. So this is that woman dancing again. You can see again her skirt swinging around as she moves, and it's captured very nicely in real time. So this type of technology will allow us to track camera position from many real-world locations and enable new types of augmented reality applications. People can also do something similar outdoors, especially using the AR cloud. So the AR cloud is a server-based cloud recognition, which allows you to create a machine-readable one-to-one scale of the real world. So you can combine input from multiple devices, so multiple cameras with phones. You can stream the video up to the cloud, and then on the cloud, you can do some image recognition and try and stitch the features of multiple devices together, and then use that to support very large-scale tracking. So for example, in this video from SIGCHI.ai, you can see 4 people walking through the real office spaces. And as they walk around, each one is capturing video from their own perspective on the mobile phone. But their software allows you to stitch all those videos together independently and create a single large model. So this is the 4 videos coming from each of the cameras. And you'll see in a minute the large model they've created. And then once you've got this very large model, you can use that for large-scale augmented reality tracking. So here's the final large model. And as I said, you can use this for large-scale tracking. So if somebody else comes back to that same location in the future, they could track their position very accurately by using this model. This is how that kind of works. So in this case, this is work done from the University of California, Santa Barbara, and they take a panorama video and they process it offline to try and find interesting visual points in the panorama. So if you're going around a campus, you might find the edges of windows or some trees or other visual features. And then once you've got those visual features, you can create a point cloud. And then when somebody else goes to that same location, you can load up the point cloud for the location. And then you can start doing some tracking and update the person's position from the point cloud. And in their test, they found that this was accurate to about 25 centimeters or half a degree and over a very large wide area, the campus area. So this is actually much more accurate than what you can get from GPS. So this video shows this working. You'll see, first of all, this is the system set up here. You'll see, first of all, somebody capturing omnidirectional video or 360 video from a little sensor they put on their phone. And as I said before, this is done offline, not in real time. So you capture the video and then you can process it to try and find the visual features. And so here's the visual features that have been captured from the point cloud. And then once you've got that, you can then use that for real-time tracking in real when you return back to the same location. So here's the person, the same location now. He's looking around. Those green dots show the visual features. Normally they would be hidden. And then he's able to put a model in space. He's able to put the Star Wars spaceship. And this tracking will work over the whole campus. So now you can walk over the whole campus and play outdoor augmented reality games or other applications due to the accurate tracking. So this is an example of how it might all come together. So this is a promo video for the Snapdragon, so the Qualcomm XR2 chip, which combines multiple augmented reality input streams. So let me just play this. So there's the XR2 chip, and this shows how it could be combined into a camera that has a head-mount display has 7 camera inputs, so lots of cameras for tracking, 3K resolution per eye, and then because it's got so many cameras for tracking the real world, they can create true mixed reality experiences, like this person running upstairs and seeing the stairs replaced by some outdoor scenery. And then he can run to his room, and then he can also play AR games in his room. Or you could have a holographic telepresence application where the person can pull in remote people into a meeting, and they can look at video together, or social applications where you can be dancing or playing with other people. This is an intelligent assistant teaching me how to cook using a virtual character like I showed you before, or this is a remote guided instruction. So all of these types of concept applications show how trends in display interaction and tracking can be combined together to provide a new type of experience. So I want to talk about a couple more research directions now. There's many areas where AR can be extended. But some of the important areas for research are around social acceptance and looking at how we can overcome some of the social problems that are associated with AR. Cloud servicing, we've already talked a little bit about cloud tracking, but being able to do processing in the cloud, authoring tools, making it easy for people to build content for non-programmers, and also collaborative experiences. So I'll talk through some of those for now. So first of all, social acceptance. A study a couple of years ago in the US, 4,500 people found that 12% of them wouldn't want to wear an AR display because they felt that it would make them look silly. And in fact, even with existing mobile AR systems, when people have to hold up a phone and walk around in the real world, 20% of people using that technology had some social issues experienced. For example, when you're holding your phone up and walking around in the real world, somebody else might think that you're taking a photograph of them or filming them. So to some extent, acceptance of the technology is more due to social issues than technical issues. And this needs a lot more study in terms of ethnography and field tests and longitudinal studies. We need to try to understand what happens when people wear head-mount displays for long periods of time, or how can we represent in the head-mount display in such a way that doesn't cause some issues around or anxiousness around privacy or other areas. There's an example of what might be a good idea, but maybe not a good idea in hindsight. Is an example of this project called Augmented ID from the company TAT, and they had the idea that you could use your phones to look at a person and have information about the person shown around them. So that might be really useful. You might go to a party and couldn't remember somebody's name, so you could hold your phone up and scan the person's face, and it will put around them their name and other information around them as well. So this is a video that shows a prototype of that system working. So first of all, you'll see the person coming home from a night out, and he's now got to get ready for work. So he's got to change his profile from the party mode into the work mode and have more professional contact information there. So you can see he's getting ready for work, and where he then looks at his real face, you can see a variety of virtual tags floating around his space. And those are mostly social, non-professional tags. So now he gets rid of some of those and replaces them with more professional tags like LinkedIn or SlideShare. So just updating that now. And then once he's done that, he can go to the business meeting, and at the business meeting, when people don't know him, they can just point the camera at his face, and some virtual information will appear around the face. So she's doing that right now, and she can see around his face these tags appearing saying who he is, and here's my links to my business site or whatever else. Now that might sound a good idea at the time, but if you think it through, it may be something you don't necessarily want to use. For example, you can imagine if you're in a meeting and with some strangers, and one of the strangers pulls their phone out and starts taking a picture of you, you might feel very nervous about that. In fact, some people that tested with this idea, one person said, well, you might feel like you're being stopped by the police for ID or security scanned, or you might be asked to show your papers. And somebody else said, anyone pointing a device in my direction to try to identify me better be prepared for either a lawsuit or a punch in the face. So even though the technology works well, there's a lot of social impediments to actually making this real for real in the real world. One of the other important research trends right now is cloud services, and we talked a little bit before already about the AR cloud and how it supports tracking. Well, companies like NVIDIA are trying to get people to do all of their, provide all the information needs through the cloud. And NVIDIA have created this consortium called the AR Cloud Consortium, and they are developing a cloud-based services that will allow you to combine service hardware with 5G to provide AR as a service. And the idea is that once you're using 5G, the network is so fast that you can have remote computers rendering the graphics, and it will look like to you like it's happening on your machine. So here's a video of how that might look like. You can see this is a VR scene, but you can see the scene, it's raining, and this is all being rendered on the cloud and then shown on the AR head-mount display in what's called edge computing. And edge computing is where you've got a very fast network connection, so you can render the graphics on the cloud and then stream the final frames through to the VR headset display, and it looks almost photorealistic. So it's very, very visually beautiful content. And this is the type of experiences you'll be able to have in augmented and virtual reality once edge computing and 5G becomes more commonplace. So and Qualcomm produces this chart that talks about the XR devices evolution, and they're saying that basically now we're using cabled devices, either cable to mobile phones or cable to PCs, or we have some standalone VR and AR headsets like the Quest and the Microsoft HoloLens. In 4 years' time, 4 to 5 years' time, we'll have a lot more wireless devices using 5G, and then in 5 to 10 years' time, you'll start seeing 5G-enabled glasses that outsource all of the computer onto the network and make the possibility of lightweight and low-power glasses really being possible. So that's talking a little bit about cloud services. The other area that we're particularly interested in my lab is improved content capture, and is collaboration. And in the collaboration, there's really been 3 important technology trends. First of all, there's a trend towards improved content capture, and this means that instead of just sharing our faces like we're doing now on this Zoom call or Facebook Live, we want to also look at sharing spaces, so we can capture the person's surroundings and stream that to a remote person. The second important technology trend is increased network bandwidth. So this is trying to share very natural communication cues. And the third technology trend is towards implicit understanding, which means that you build machines that can recognize your behavior and emotion. So just to talk about these a little bit more. Oh, and these three overlap actually. So you have the three overlapping areas of natural collaboration, experience capture, and implicit understanding. And in these overlapping areas is the space that we call empathic computing. And so that's the focus of my research lab, is the empathic computing lab. So the goal of empathic computing is really to answer this research question. Can we develop systems that allow us to share what we're seeing, hearing, and especially feeling with others? So of course, with Zoom and other technology, we can share what we're seeing and to some extent hearing with other people. But it's much more challenging to share what we're feeling with others over long distance. So in order to show you the types of projects we can do, this is one of the projects we did as part of the empathic computing lab. This is called the empathy glasses. And the goal of these was to provide the same implicit communication cues that we have in face-to-face communication, using eye gaze or face expression to communicate. So these glasses combine together eye tracking with an AR display and also with some face expression sensors that allow you to know when the person on the other end is frowning or whatever else. And we combine them into a single form factor. So you see on the left the person wearing the technology. And we want to use this for remote collaboration and be able to use this so that the person wearing the technology can share their eye gaze with the remote person helping them, and also can show some face expression. And this is important because in face-to-face communication, eye gaze provides an implicit non-verbal communication for remote collaboration. So you can see on the right-hand side here, the interface that we show inside the AR display. You can see there's a set of blocks the person's using, and then there's a green dot there. The green dot represents the remote pointer from the person who is providing some assistance. And then most importantly is this red dot. The red dot here represents the eye gaze of the person wearing the technology. And so what that means is that now you can share these non-verbal cues of pointing and eye gaze remotely. We also have on the bottom right-hand side a heart rate sensor, and the bottom left-hand side some face expression detection. So just to show you this working, you can see in this video the person wearing all the technology, and he's performing a remote collaboration task with some bricks, so assembling these bricks together, and he's doing it under the guidance of this remote user. So the person who's remote can use the mouse pointer to point at objects, and as he moves the mouse pointer around, the green follows where he's going. And then most importantly, the red dot shows the person who's doing the work where their eye gaze is. And so the remote user can tell exactly where the person who's doing the work is looking. And we did that by combining the eye tracker with the AR display, and also a facial expression sensor. This is a facial expression sensor here using photosensors to detect the skin movement. And what we found in this situation is that by sharing eye gaze, the remote person felt a lot more connected to the person doing the task. And of course, people always look at objects before they move them. And so the remote person could ask the person to do something, and he would know whether the person was able to understand or follow them or not, because the eye gaze would be following where the pointer was going. So that created a much higher degree of social presence or connectedness. One of the other areas that we're looking at, which is very exciting, is looking at this area of brain synchronization. And so brain synchronization is a topic which has been studied just really over the last 10 years in psychology. And the idea is that when people perform a task in the real world, for example, on the left-hand side here, you can see two people sitting opposite each other, pointing their fingers at each other. And when one person moves their hand, the other person is supposed to move their hand to match it. So this is a task in the real world. When people perform this task, we can measure their brain activity using EEG. And in many cases, we find that the phase of the brain activity synchronizes. And when that happens, people feel like they're connecting more and they're collaborating better together. So on the right-hand side, you can see people doing the same thing in virtual reality. So let me show you some results. So first of all, this is what it looks like measuring the brain activity of people. You can see there's two heads here, and these black dots here represent where the EEG electrodes are. This is before they've started moving their fingers or doing finger pointing. And then we ask them to do this finger pointing task, and then we ask them to stop moving their fingers. And when they stop moving their fingers, you can see these arcs now going between each of the heads. And these lines represent the points on the EEG electrodes that are in phase with the other person's other head. So we can see that now we have some brain synchronization happening. We're trying to do the same thing inside virtual reality. And so here's two people in the VR setup. Of course, in this case, they are both using virtual characters, so you don't need to look at each other anymore. This is what you see inside VR. So you can see your own body. When you look across the room, you can see another person pointing at you, and your goal is to try and keep your two hands aligned. So that's in VR. But of course, one of the great things about VR is that you can put your body inside somebody else's. So we did a follow-on experiment where we took the two avatars and put them in the same viewpoint. So you can see that here. And now when we look down, you see two pieces of hands coming out of your body. And they, again, you have to follow the other person's hand motions. But the benefit of this is that you both have exactly the same perceptual and visual cues. And what we found was, again, we had this very strong brain synchronization. So this shows the activity of the brain before we start the task. The blue lines here show the electrodes, which are their phases connected, but this is a very low level of connection. So this is mostly due to noise. But then when we do the task, we see this band activity happening. And here we have very strong red lines and purple lines. And these ones show areas where you've got multiple electrodes synchronizing to each other. And so this shows very strong activity in brain synchronization. So in the technology space, we can see a number of trends happening in AR and VR. Of course, there's trends towards better displays, high field of view and high resolution. Also towards real-time space capture, so being able to use handheld or head-worn technology to scan around and stitch together to make the spaces. There's also important research being done on natural gesture interaction. So hand tracking or human-imposed activity recognition, so if you're running or standing in certain ways. There's research on eye tracking, where you can measure the gaze points where people are looking, also their focal strength. And then finally, most importantly, what we're interested in is measures of physiological sensors, where you can use that to measure emotion and map the emotion back into the shared physiological state. So these 5 areas are really important areas of technology trends. And what we're seeing is that these can be pulled together into what you might call empathic teleexistence. So the idea of empathic teleexistence is that you have two people or more working with each other, and they move from being an observer to being a participant. Or the communication changes from explicit communication, where you have to tell the person what you're doing, to implicit communication, where you're just watching the person doing something and you can the system can respond to it. And so overall, this creates this experiential collaboration where people feel like they're doing things together. So as an example of what that might be, like an experience of that, there's been some research being done on empathic teleexistence and putting people into the bodies of robots. And so this really could be one way that you can really know what somebody's seeing, hearing, and feeling is to go into the same body as them. And this enables you to feel like you're in the same environment. And you can also see virtual people with you in your real world through the eyes of this robot. Now, this may sound like a big science fiction or fantasy project, but actually there are people trying to make this real. But it has been shown in science fiction. And this video here, this is from a movie called Surrogates. It was a Bruce Willis movie that came out 10 years ago. And the premise of this movie was that in the future, robots would be very cheap and we'd all be able to have our own robot. Then the robot can do things like go to work for us or do dangerous things like it can jump off buildings and so forth. So here's Bruce Willis in VR driving his robot. And this is the Bruce Willis robot. You can tell because you've got the blonde hair. And then here's one of the robots jumping off a building and doing some other dangerous activity. But what started happening in this world, until that time, nobody was ever getting hurt because they were just in VR driving the robots. But then for the first time, people started killing the robots. And when the robots died, the people in the real world driving them also died. And so the main idea of the movie is it's kind of a detective story to figure out why these robots are dying and who's doing it, and what can be done about it. So that may seem like a science fiction fantasy, but there are researchers looking at how they can make that real for now. So for example, this is a video from the company called TeleXistence. And TeleXistence builds a real robot you can drive with virtual reality. So here's a person putting the virtual reality equipment on. And when he puts the head-mount display on, he jumps into Hawaii. And you can see as he looks around, he's looking around inside a surf shop, and he's trying to buy a surfboard. So he's pointing out the surfboards he's interested in, and you can actually reach out with the robot hands and feel it, and then the virtual reality gloves have some tactile sensation in the gloves as well. He's taking a selfie picture with the robot. And the idea of TeleXistence is the robots are very expensive, so they typically cost $100,000 or more. But their idea is not that everybody buys robots, but you rent time on the robots. So you can jump in different robots. So now he is with his son jumping into a different robot in Kyoto, Japan, to see the cherry blossom festivals. And then they decide they want to go to space, and they can click there and they can connect to a robot which is on the space station. And then they feel like they're just floating in space as they're looking around at the scene below them. So this is an example of one possible future about how combining these technologies together, empathic computing technologies with other technologies may allow us to have these type of rich telepresence experiences where we feel like we're really somewhere else inside somebody else's body. So that's pretty much all I want to talk about today. I've talked a little bit about how augmented reality is becoming much more commonly available, and if you've got a mobile phone, then you've got the technology in your pocket to be able to have an augmented reality experience. But to have more significant growth, augmented reality needs to expand into new markets and new platforms and create new types of applications. And to make this happen, there needs to be new technologies developed. So we've talked a little bit today about technologies with displays, interaction, and tracking. But there's also significant areas for research, the social acceptance, where you want to look at to see whether the technology is socially acceptable. Cloud services, where you can outsource a lot of the graphics or tracking needed. Collaboration tools and others as well. So this was based a little bit on a paper I just published earlier this year. So if you're interested and want to find out more, you can read this paper called Grand Challenges for Augmented Reality. And I talk there about some of the challenges in the areas of display interaction and tracking that need to be solved in order for augmented reality to become more widely available. I should also mention, if any of you are interested in this, then we have some virtual internships available at our laboratory. We had one deadline earlier in March this year. We've got another deadline coming up in July. So if you'd like to do an internship with our lab, you're more than welcome to apply. These virtual internships means you can stay in your own university or your own home and do internships remotely with our students in the lab here. And then I should also thank, finally, the ACM. Of course, you're an ACM chapter, so you know a lot about the ACM. I've been an ACM member for a long time, and I'm very happy to be a member. And I'm very happy that ACM provides the Distinguished Speaking Program that allows people like myself to come and talk to you. So this talk was made possible through the Distinguished Speaking Program. So that's everything I wanted to say today. I've certainly got some time now for questions. And if you want to find out more about the research we do in my lab, then feel free to visit our lab website or email me or follow me on Twitter. And I'm also happy to send copies of these slides to anybody who wants, so you can re-watch again the videos or find out more about what we're talking about. So thank you very much for your time, and I'll stop my slide sharing now, and I'm happy to take some questions or have some discussions.
Thank you very much, Mark.
Thank you so much.
Great to hear my familiar research, but also
yes, it was your
topics
yeah.
as well. Yeah, a lot of new things I learned today. So we have a couple of questions actually sent through on chat. So I'm going to read out the first question. would you like to take a short break, like a minute to drink some
Oh,
water or something?
that's okay. It sounds fine.
Okay.
I'm feeling good. Thank you so much.
Okay. Yep. So first question from Facebook is technology has been increasingly advanced, partly because of COVID-19. So people work remotely and have least physical interactions. What about AR, VR world? Do they actually benefit from, I guess, this event? I mean, because of the pandemic, and why do you think that is? I guess the answer is quite obvious, but would like to hear your point of view from the situation we are currently in during this pandemic. What do you observe? What's the change? What has changed, and what's the state of the industry and research in AR, VR?
That's a very good question. So first of all, in many ways, the pandemic has forced everybody into a big experiment. And for most people, they've been doing a lot of their work online. And for myself, I've been teaching my university classes remotely through Zoom. And so we've discovered pretty quickly some of the limitations of current video conferencing technology. We get very tired if we sit for 5 or 6 hours a day on online meetings. And that's because we lose a lot of the spatial cues. And so augmented and virtual reality can help bring those cues back. And certainly we've seen a lot of increased take-up of AR and VR conferencing. There are a number of applications. For example, there's a very nice AR conferencing application from a company called Spatial. And Spatial provide a way for you to see remote people in the real world around you. And it makes a much more different conferencing experience than just having a Zoom call. There's also some social VR applications. Facebook have been beta testing their Horizon platform, which allows you to do large-scale social VR. And some people have been using things like Outspace VR from Microsoft to have social VR experiences. So all of those have grown a lot during the pandemic. And I think part of it is because people really want to have the experience of sharing a space with somebody else, either an online virtual space or having a remote person come into their a real space and feel like they're really there. And you don't really get that with a Zoom call. So it's very, very good for us that are doing research and collaborative AR and VR, because there's a lot of now emphasis on how we can improve those shared experiences. So and so I think you'll see a lot more of those types of social AR and VR experiences coming in the next few years as a result of what we've learned from the pandemic.
Thank you, Mark. Hopefully that answer your question. I think that question is from Mintra. Sorry, I haven't mentioned that. Next comment is not quite a question, but it's more like a comment on the previous question, and it's to do with how the system, AR, VR system can actually help in teaching and learning, as you said just now, about like giving lecture through Zoom, but then is not as immersive and unlike face-to-face. The next question is around the interaction. So because in your lecture, in your keynote just now, you talk about the 3 aspects of AR, and one of them is interaction. This question is from Ibrahim Mohammed, and basically he asked that he felt like keyboard is the most effective way for input, especially I guess text inputs. Do you have any comments on that?
Oh, that's a good question as well. So certainly for some tasks, keyboard is very effective, but it depends on the task really. If you're writing a paper or a document, then definitely keyboard. But if, for example, you're trying to learn how to take apart an engine, then it may be very difficult to type commands in on a keyboard to learn how to take apart an engine. It may be much more efficient to use your hands to pull pieces of the engine off and do it in an AR or VR setting. So one of the challenges in the past has actually been to bring keyboard interaction into AR and VR. Of course, with augmented reality, because you can see the real world, you can have people typing on real keyboard, but some people have also been trying to use a virtual keyboard. So when you're walking around in the real world, you could have, sometimes you see in movies, you have these virtual keys appear. And one of the challenges with that is that you can't feel the real keys, and part of typing is being able to feel the key press, and taking that feeling away means it reduces the efficiency of the keyboard. So it's actually a very active area of research on how to bring keyboard input into AR, especially for those cases where you want to type documents or commands or names. And people are still trying to find the best way to do that. It's been very hard to achieve the same level of typing as you can with the physical keyboard. In our research, in our lab, we've been doing some research on bringing real objects into VR environment. For example, you know, if you're in VR, you cannot use your real mobile phone because you cannot see it. And similarly, you can't use a real keyboard because you can't see it. So we've been doing some work on how you can use computer vision to allow people to see real objects and bring them into VR. So that might be one way to use a real keyboard again. But I think overall, the people are trying to look at the interaction methods that are best for each task. So for some tasks, keyboards are very good and they want to use them in AR. For other tasks, they may want to use gesture or speech or other input methods as well.
Thank you. Our next question is from Saram Nurani, and the question is, in some parts of the world, the internet is extremely slow. How would you suggest a more suitable setting for remote AR, VR for education and learning with this low bandwidth?
Oh, that's a great question. So, you know, in my house in New Zealand, I'm lucky to have a high bandwidth connection. So that means I can stream, you know, 4K video or have very high quality video conferencing, but not everybody has that. And so, you know, if you're in a remote location, you maybe cannot have a good Zoom connection because you don't have that high bandwidth. So there's some very interesting research that's been done lately on how you could use virtual avatars. So it turns out that instead of streaming a high bandwidth video, you could create a virtual character, and you just need to, first of all, when the person starts the application, they can download a 3D model for the character. Once they've downloaded that model, then they don't need to send a massive amount of bandwidth or data to animate the character. They just need to send small updates. For example, if the character changes face expression, you just need to send small amounts of text to say the character is now smiling or have different face expression. Or if the character is moving, you need to send a small amount of text. So I saw a very interesting project that just came from NVIDIA, where they talked about how they could create a virtual character on your local computer using machine learning techniques. So they would record a short video of you speaking, and then based on that video, they'd make a 3D character, and then the character would be looking almost photorealistic compared to what you were like. But the amount of bandwidth they had to send over, I think, was 100 times less than what they would normally need to send through video conferencing, or maybe even more like 1,000 times less. So that means that it was very, very bandwidth effective. One of the most important things that we learned, though, and a long time ago, I did some research on video conferencing in low bandwidth situations, was we learned that the most important thing was to make sure you have a very good audio connection. So even if the bandwidth is low, you want to make sure that people can still hear very clearly. And if they can hear clearly, you can have low quality graphics and they can still collaborate quite easily. And so that's an important lesson to be learned. So even with low bandwidth video or video but low bandwidth connection, if you have a virtual character to represent the person and have good quality audio, you can still have a good quality experience. Now I wanted to put, just trying to see here.
Yep.
Yes, I just found a video of what I was talking about working, and if you want, I can show the video of that working. So
that would be great. Thank you.
Yeah, so let me just I'm just gonna, it's just on YouTube, and I'm just gonna pause the video and I can share my screen. And let me just see, is this the right one? Yes, okay. So and so it kind of shows what the power of having high quality machine learning. So let me just share this. So in this video, what you will see is it's using a cloud AI video stream platform. So this shows on the left-hand side, this is a 360p, so low resolution video being streamed. Then on the right-hand side, this is upscaling it using machine learning and making it much higher quality. But you don't have to share all that bandwidth. You just have to do it all locally. So it makes it much higher resolution, very much higher resolution video. And I think also a bit later on, you can see as you go from left to right, the person looks much clearer. And then I'm just going to fast forward a little bit. I did something else. Oh, yeah. So this is an example of using a conversational AI character. So this is an alien that speaks like you, and in this case, you really have to send almost no bandwidth because you just have to send the mouth shapes over. And I wonder if they've got. Yes. So this is an example, if we go back a little bit more here, of doing extreme compression using AI. So you can see on the left-hand side, they're using 100 kilobits per frame on normal video compression. And on the right-hand side, it's 0.1 kilobit per frame by using the augmented reality, it's AI to do video compression. So you can see that's reducing by 1,000 times the amount of bandwidth you have to send. And the result is looking pretty good. And as I said before, if you have very good audio, then you can still have a very good communication. So NVIDIA is doing a lot of very interesting work in how you can use machine learning combined with AI to dramatically enhance the video conferencing experience.
Thank you, Mark. And I can imagine as well with today technology like from Unreal with MetaHuman, when you have realistic avatar, you can just track several feature points on user's face, right? And then just send that.
Yes, that's right. And that's what happens with the other example I was saying about where they build a virtual avatar of you, and then they track the points on your face and just send the points over. So the amount of information you have to send is very, very low compared to using a full high definition video conferencing. Yeah.
We received another questions from Ahmed, and Ahmed asks if leap motion is still relevant today since it seems to be superseded by other technology, and is it like going to be useful to integrate and look into leap motion for research today?
Yes, so that's a good point. So leap motion is old technology. I mean, it's still being updated, but nowadays, especially with the Quest 2 and the HoloLens 2, there's some really interesting work doing on hand tracking without having to use special infrared sensors like leap motion uses. So now you can do some amazing interaction just using your real hands without having any special sensors like leap motion uses. So it is old technology. The important thing though is that even though it's old, you can still use it to prototype some interesting interaction methods. And because it's so old, people have built a lot of examples and software that you can use to integrate into your projects. And so you can prototype ideas without having to do a lot of computer vision programming. So that's one interesting element is that when you're doing this type of research, you want to try and prototype ideas as fast as possible, and well-proven technology like leap motion allows you to do that.
So that's all the question we received from Facebook. For me personally, I have like my own questions since we still have time. So I guess we can ask my personal questions. So I guess over the past several years, we have looked at improving fidelity in terms of like visual audio to achieve the tele-assistant. How about the other sensory, in your opinion? How is it coming along to actually make it even more immersive?
Oh, that's a great question. So I think a lot of research has been focused on the visual fidelity. And part of that is because, humans, most of the input we receive is from the eyes, the vision senses. But there's a lot of other important areas that we need to focus on also for immersion. So, for example, the sense of touch as well, and smell, and even taste. And there's been interesting research in those areas, but they lag behind the visual quality. One of the areas which I think has not been as well researched is audio, and in particular spatial audio. And in some games they create spatial audio experiences so you can hear sound around you, but it's not used very often in everyday conferencing. It will be very easy, for example, with a Zoom conference call, to have a spatial audio call. So when you've got 10 people on Zoom, they appear spread around you rather than all coming from the same source. And in fact, maybe 15 years ago, we did some research in my previous lab about that, and how you could hear, when you took the spatial audio and spread it, you could create a more immersive conferencing experience and have multiple people speaking at the same time, and still hear them all speaking at once. And so it'd be very easy for people to add more immersive audio experiences. And then the other senses are more difficult. There are people who have been working on haptics for about 25 years or so, and they're getting to be the point where you can, with a haptic arm, you can feel a good sensation, but it's really hard to have that in gloves, for example. And I think smell is very difficult. Some researchers have been doing some work on olfaction and creating sense of smell, and they have little vials of perfume that they'll open and close, but it's very challenging to create arbitrary smell experience, because unlike color that has primary colors, there aren't really a small number of primary smells you can mix together to create that. So I think we've got a long way to go, but which is positive in one sense. That means there's still plenty of opportunities for collaboration and research, but still means that for a while anyway, our VR and AR experiences will still feel quite different from being immersed in the same real space as a person.
So last question, follow on from that previous one, talking about Elon Musk, like Neuralink.
Oh yes.
Do you think the technology that will give us full immersion, the external one, versus something that bypass like our peripheral, nervous system, which one do you think would come first in your prediction?
Oh, it's hard to know. I think certainly visually, within the next few years, we'll be able to create visual experiences that are almost indistinguishable from the real world. If you play computer games and you've got a high-powered graphics card, you can already, in fact, you can already have experiences that are almost indistinguishable from the real world. In fact, I saw a demonstration from Intel, I think, a month ago, where they showed how they could use machine learning to create a real-time driving simulator that looked indistinguishable from driving through the real streets of Los Angeles. So we're almost visually there in terms of becoming indistinguishable visually from the real world. But we've got a long way to go on the other haptic and other senses. Now, of course, what Elon Musk is looking at is embedding technology into our heads to directly stimulate the nervous system, and in some ways jumping over our sensory organs. And of course, the eyes typically take visual light and map them onto electrical signals in the brain, and what he's trying to do is create those electrical signals directly. And I think that's very interesting, but it's going to be probably, I imagine, 15 or 20 years before you can create or have a lot of control over the full range of sensory signals that we get into the brain. It's a huge engineering problem, and I can imagine that it's there was a lot of ethical and complicated issues to be resolved in that case. One thing, of course, though, is that if you've got people who have a variety of disabilities, like a visual disability or cannot walk, then they may be very that could be very exciting for people in those cases, because they can't see anyway or walk normally anyway. So having a brain implant will be able to restore lost ability. But if you're trying to create something for somebody who's already fully abled and then somehow replace their experience of the real world, then you better make sure that what you're doing provides at least as good experience that they've already got, rather than reducing what they have. So I think the adding to their existing senses will probably win out in the short term, but in the long term, maybe 50 years or so, then that I guess it's getting towards what you see in the Matrix and other movies, where you plug yourself into the computer and it takes over all of your sensory organs. But I think I'll be long time dead before that happens, so I don't have to worry about some of the ethical issues around that. It's very challenging. So yeah.
But at least we have kind of at least the minimum prediction from you, like 15 years. So
well, we'll see what happens. Yeah.
Hopefully we can, like, you know, for next, like in what the 18th Thai SIGCHI, we can re-invite you again to give a keynote and talk about this prediction.
We'll see what happens. But I mean, it's a great, exciting thing is there's great areas for research. And so those of you who are listening that are students, you can think you've got a lot of exciting topics for doing future research in AR and VR in these areas, which is lots of pretty positive areas for doing research there.
Yeah, thank you so much, Mark. I always learn a lot from you, and I'm sure everyone here also enjoy your talk and been enlightened.
Thank you so much for the opportunity. Yeah, and if anybody has any other questions, please just email me, or I'm happy to answer in the future. So thank you so much for the opportunity. It's a pleasure to be able to speak today.
Thank you. Oshin, would you like to take over? Maybe you should bring some water, Mark. It's like 2 hours. Yeah,
that's true.
Even I feel thirsty for you.
Thank you. Okay, thanks so much.
Okay, so I think Aim is taking over.
สวัสดีค่ะ ได้ยินไหมคะได้ยินสวัสดีค่ะ
Yep ได้ยินครับ
ค่ะก็ขอบคุณนะคะวิทยากรท่านแรกนะคะแล้วก็ขอบคุณพิธีกรคนแรกให้ด้วยนะคะก็อันนี้นะคะอยากจะขอเชิญชวนทุกคนนะคะที่ตอนนี้ดูไลฟ์อยู่ก็คือว่าสามารถเข้ามาตอบแบบสอบถามนะคะก็คือขึ้น QR code ไว้ให้แล้วถ้าใครไม่สะดวก QR code นะคะสามารถคลิกลิงก์นะคะมีให้อยู่ที่ตัวคอมเมนต์ของ Facebook เรียบร้อยแล้วนะคะ